about the results on the global geometry of Scalar Curvature.
Thank you for the invitation. It's always a pleasure to return to Stony Brook. So, as advertised, I'll talk about some new results about this global geometry of scalar curvature. And I wanted to begin by sort of trying to describe the point a little bit of some of the things I've been doing, and I have to, so I have to apologize because certainly when I put this up here, there's people, in the room who have contributed much more to this question than I have. But sort of to set the stage, what I wanted to talk about is that in Riemannian geometry, we have this notion of sort of how does a manifold curve at a local scale. So curvature you can think of as, I think everyone knows intuitively what curvature might mean. And sort of a question that's been around for a long time, as old as the subject itself, but really in the last 100 years it's been studied to great success, is sort of how do you, if you go from this local quantity, which is curvature, how do you ask something, say something that is global? And so, okay, so obviously this is too big of a topic for me to discuss or to be my research, my topic of research. So what I wanted to focus on today, and some of the things I've worked on recently, is a more precise question. So when you say curvature, I think everyone has some sort of notion about what it means to be curved. But if you've taken a Riemannian geometry class, you know that saying just curvature is not really very precise. So for me, I'm going to focus on what's called scalar curvature. Okay. So the question, sort of all the things I'll discuss today are hopefully going to go towards partially giving you a feeling of what does this scalar curvature, how does the scalar curvature influence the geometry of the manifold at a large scale? Okay. And so scalar curvature is it's sort of the weakest curvature invariant you can write down. And so I'm going to go back and forth between sort of comparison with Ricci curvature versus scalar curvature. May not be very useful if you don't have sort of some feeling about what Ricci curvature is, but you should think of, so Ricci curvature is some sort of, you could think of it as like a matrix quantity. And so we're going to sort of think about things where you're assuming something about the trace of a matrix versus sort of a positivity of the whole matrix. So going from Ricci to scalar, just sort of as a definition, you've already seen that you've averaged out a lot of information. And the problem with trying to study scalar curvature is that it doesn't do a great job of transmitting information at a distance. So I'll try to make this a little bit more precise later. But really, to sort of, it's taken a long time to eke out how scalar curvature influences different points on the manifold. Okay? And so with Ricci curvature, this is much more transparent in some sense. So I'll try to draw the analogy between these two. So scalar curvature is one way to define scalar curvature, for example, is that if you look at a geodesic ball, so these are all the points which are a distance at most r from the center, and you measure its volume, so because you have a Riemannian metric, you have both a volume form and a distance function, put these together, you get some volume, and hopefully so Riemannian manifolds look Euclidean at small scales. So you look very flat. If you use your magnifying glass and you zoom in, you look like sort of flat Euclidean space with some perturbation. Right? The perturbation is where all the interesting stuff happens. And so exactly, this is supposed to be the Euclidean volume, okay? And scalar curvature, which I call R or P, shows up at sort of the first non-trivial order of correction.
Cool.
All right. So
define.
Yeah. So there's our definition. So what I want to I'll try to go back to sort of Ricci curvature and compare the two things. And so Ricci curvature is, remember, this is like the thing you trace to get scalar curvature. This tells you something about the volume at all sizes, right? So if I take a ball of radius 100, I can estimate its volume by and notice, sorry, this is the Euclidean volume of a ball of radius at r, and here's the metric volume of the ball of radius r. Okay? And so, in some sense, this is all you're going to hope to get. Notice that this expansion doesn't even imply that if you
That
have...
works for both sides.
Excuse me?
That one works for both sides.
Yeah.
Well, but it actually doesn't even imply this.
No, I know.
It only applies in the limit.
I know.
Sure, but you're exactly right.
General.
Sure. So yeah, there's a bit of a funny story that the curvature conditions I'll talk about today. It only is ever going to really make sense to look at lower bounds. So for scalar curvature, we're only going to ever really look at lower bounds. And I think I don't know if I can manage to explain why. And so, okay, so we just saw there's some relation between scalar curvature and volume. Okay, and so to continue with our sort of volume kick, I wanted to talk about the Iso-Parametric problem. Okay, so I think the Iso-Parametric problem is quite a classical question about mathematics, at least in flat space. So we say that a region is isoparametric if it minimizes the surface area among regions enclosing a fixed volume. So I draw a picture.
So the surface of a region, you mean?
In minus one dimensional.
Yeah, so for me, everything will be, let's stick with 3 manifolds. So
All like the region.
So here's a region omega and the boundary. Okay, and then if I do some change, so if I have some other region, and I've somehow changed omega, I mean, the change could even be sort of completely, I delete this and draw a new region over here. If I do any change which preserves the enclosed volume, then I must increase the surface area. Okay? And so in various guises, this sort of fact, so in Euclidean space, the round balls are the minimizers for this problem. So you enclose a fixed volume, say what's the least area? What region encloses a fixed volume with the least area? And so this sort of fact is known, I think, for example, in R2, it's definitely known by the Greeks. Proven rigorously is more recent, but so it's quite a classical fact. And so one thing I should say, which I think is not a priori obvious to someone who hasn't investigated this sort of thing, is that the situations where we understand what are the isoparametric regions. So there are some situations where we can give some estimate on the area of isoparametric regions, but if we say we want to really know, like, what are the isoparametric regions?
What about knowing they exist?
So knowing they exist, probably should have put that on there. If the manifold is compact, then they always exist, containing any volume. In high enough dimensions, there could be some singularities, but depending on who you ask, we understand them well, or there's also many questions we still don't quite. But we have some level of understanding of the singularities. But in non-compact manifolds, actually, which is what I'm going to talk about in a bit, even existence is not clear. So there are cases when there's no existence, there are cases when you can prove existence. So even existence is sort of already a hairy business. So just to say just to give you some examples of where we understand things, in the sphere, hyperbolic space, Euclidean space, we know that they're geodesic balls. Okay? And some quotients, for example, some quotients of the sphere, we know what the isoparametric regions are. Actually, like last week, for certain lens spaces, it was solved, but only last week it was solved for lens spaces with very large fundamental group. You could describe the isoparametric regions. Some products and some things with a high degree of symmetry. But so my favorite example to try to convince people who maybe have never looked at this that we don't know that much about these things is, so even in you take CP2, which I think there are people in this room who would claim we know everything about CP2, maybe, I don't know. Right? And so in CP2 with the canonical Fubini study metric, we don't know what the Iso-Parametric regions are. So like well-known. So just sort of.
I mean, you know some of them, but you don't know. You don't know. You don't.
So I can describe them
down any one concretely.
So I can describe the Iso-Parametric regions for very small volumes.
Very tiny ones.
Very tiny ones. But if you take the volume which is half of the Fubini study volume. I mean I could guess. I can tell you what I think it is, but you don't know. You can't prove that there's not something there. So
sort of related to the pathological behavior of Barry Shakespeare's when they're.
Wait, you see something? Yeah, it has some relation with the Barry Shakespeare's.
What's your guess?
There's a couple. You can try to lift things to the sphere, and I don't want to. Maybe I won't go on record, but there's some obvious candidates like the Clifford torus in the sphere that has the it looks Iso-Parametric. It smells Iso-Parametric, but I don't know if
it's made out of these great circles, right?
What's that?
It's made out of great circles.
Yeah.
And then it goes down nicely.
Yeah. So okay, that's my guess, but it's not clear. Somehow the problem is that most of the proofs we understand involve either you study surfaces. So for when you're studying things in three manifolds, sometimes you can use something like Gauss. You have Gauss-Bonnet, so that's going to help you. And so here you're not, a hypersurface in CP2. Everything for me is real hypersurface. It's codimension 1, so there's no Gauss-Bonnet. You've lost that tool. But then CP2 is very symmetric. But from the point of view of the Iso-Parametric problem, it doesn't quite have enough symmetries to do some sort of symmetrization argument. And so your short list of tools sort of runs out very quickly. So, okay, so maybe I've convinced at least a couple of you that this is a problem with which we might try to investigate further. And there's sort of a nice link with scalar curvature and your question, actually, which So it turns out that if you look at small volumes in any say compact manifold, then we can understand very nicely how the Iso-Parametric problem for small volumes acts. Okay? And it has a nice answer, and it's related to scalar curvature. And so, in some sense, this is one of the only results. I was trying to think on the. You don't want to claim that this is the only result because probably there's something out there that I'm missing that I'll offend someone. I'm on video. So it's one of the only results where you can say something about the Iso-Parametric problem that doesn't apply to sort of quote unquote special manifolds. So this applies even to any manifold. And I haven't stated the theory, but I will.
When you say any manifold, you assume compactness?
For here, let's assume compactness. You can push this a little further. And so this is due in various forms to sort of this list of people.
What decades? Nowish?
Last 30 years. I think I actually don't quite know. I'm guessing is the sort of thing that people suspected for a long time and then was proven in the last 20 years.
Does it start with C2?
What's that?
Does it start with C2?
What do you mean?
Smoothness?
I'm not sure what the optimal smoothness. You probably could get away with C1 alpha. I'm on video again. I don't want to make. But you don't want to. Well, I guess with C1 alpha, the scalar curvature is not even defined. So maybe let's guess C2, probably C4.
Well, Gromov, who spent his career here, used to always emphasize that C2 means that in the small, everything looks nice and convex.
Yeah. So I think you're somehow going to use.
From that into me. Yeah.
You're going to somehow use a derivative more than that, I would guess at least. So before stating the theorem, I sort of want to just describe how you might analyze small Iso-Parametric regions. So, okay, I just asserted to you that there's existence in a compact manifold. Let's not. That's relatively easy now that we have some technology. And so, once you have existence, then you can try to sort of characterize the small one. So, what I'll do is I'll take a small one. There's no reason I've drawn it like this, but maybe it has multiple components. Maybe it splits, has tentacles, things, etc. And so, okay, I'm only interested in the really small ones. So I'm going to look at smaller and smaller. All right, so it's getting pretty small. And so now I'm going to use, now that I'm really tiny, I'm going to use this fact, like what you just said, that because we're so tiny, the manifold looks very flat nearby. So if we sort of zoom in around this Iso-Parametric region, and so, okay, I'm lying slightly, there might be multiple points of concentration, but actually this argument is going to simultaneously characterize what they look like and rule out multiple points of concentration. So, okay, so somehow, like after the fact, this is really the argument. There are some other things which I'm worried. And so, because when I zoom in, the region, the isoparametric region, is now an isoparametric region in something which is very close to Euclidean, then because in Euclidean space, I know what the isoparametric regions are, they're round balls. So here I know I'm nearly round. Okay. And so
it couldn't stay definitely away from round because you just take a limit.
sure, yeah, in the limit it's exactly round.
So it can't stay away from round.
Sure, no, that proves that. You have to worry that there's two regions, for example.
Oh.
That's a bit of a fear, but you can prove that if there are two regions, then both of them would have to be roughly the same size. So that's sort of because they have the same curve. You know that just from the variational argument, you know that two regions would have the same curvature. And if they're the same size, then you look like two balls in Euclidean space. And two Euclidean balls are much worse if you just compute their area. It's much, much worse than one.
So for this argument to work on the face of it, your definition of minuscule involves small diameter, right?
Well, really I mean small. Okay, so there's some tools which I'm sort of suppressing. So it's all small. I really want to use small volume because for this, you don't want to talk about diameter. So somehow, if it turns out that when the volume becomes very small, you're worried, I guess, that there's like some tentacle, right? But somehow such a tentacle could be snipped. So you could prove that this would be better than that. And this means that sort of these tentacles are not, because you're sort of a minimizing area, the tentacles are actually not there.
It could be droplets. So.
But actually, I know that any droplet, even if it drops off, it would have to look quite round, and then it would have to have the same curvature. So you play this game and you start ruling out anything besides exactly this picture. So I sort of skip some of those. And so now I have some metric which is very, very close to Euclidean, and I have some region which I can imagine is like a radial graph whose function is very, very small. We're very close to constant. And so then you can do the technical term, like a sort of Lyapunov Schmidt reduction. So you use that you can very, very well approximate once you center, you choose the right center. You can very well approximate this by a sphere, and this lets you compute an expansion for the area in terms of the volume. Okay. And so, obviously nobody wants to see me do this. I think even the experts don't. No one really enjoys. Maybe some. I shouldn't say that again. But this computation is quite technical. But the idea is that you go based off of the Euclidean.
Wait, I see that 2 over n power there.
Where's that?
The second
Here.
the volume.
Oh yeah. So let me make some remarks. Okay. So before I get to the 2 over n, notice that the leading order, because volume is very small. So if you look at which is leading, this guy is Euclidean. Okay, so this is the Euclidean isoparametric ratio. All right. Hopefully I haven't made a mistake in my form. So as expected, the isoparametric region is approximately Euclidean to top order. And then there's this correction. And this volume to 2 over n is like radius squared, I guess. So that sort of corresponded to the previous thing. And you have to do this computation. You have to be quite careful that the sign comes out correctly, and you see that it's a minus. The minus sign is important, and nothing else really is so important for this thing. And so now you could imagine that why does the isoparametric region prefer the point that it concentrates about? And now you sort of see, okay, to top order it's Euclidean, so every point is the same. But the next order is the scalar curvature. I guess I should have said that this is the scalar curvature. Okay. And so you see that the isoparametric problem, because you want to minimize the area, you want to center around the point of maximal scalar curvature. Okay? Okay, and then here's the theorem. So small isoparametric regions are close to small geodesic balls, close in some rescaled sense. And they're centered near, I guess writing at is slightly a lie, but centered near points of maximal scalar curvature.
Sorry, you're assuming positive curvature?
No, this is like, the beauty of this theorem is that it applies to anything.
And why, if R is negative?
But could be
What?
less negative at some point?
Yeah, so you pick the least bad. You have only so many options. You have to pick one. Pick the one best. I think there's a lesson in politics. So, all right, I won't make it more. Okay, so yeah. Does that answer your question? Cool. So, okay. Okay, great. So we sort of discussed the isoparametric problem and how it relates to scalar curvature for small volumes. And so, okay, you come along, you say, great. What about slightly larger volume, right? This only worked at a very small scale. And so, as I alluded to, you probably can't answer this question. You can't make some grandiose statement about scalar curvature and the isoparametric problem of the large.
You said they exist.
They do exist, but yeah, okay. But then what do they look like? How do they behave? Can you do anything with the curvature?
So right now you don't have an effective statement about how large the diameter of the ball is so that it is in fact.
No, actually I don't think that is clear. Like there's a constant depending on the manifold, so that for something smaller than that constant, I can say what it looks like. Approximately, the approximation gets better. But everything you prove here something by contradiction, and I think the contradiction is somehow taking care of the volumes which are big enough to be affected by some more global geometry. So yeah, it's definitely not. I don't even think there's an effective. I mean, you could make some compactness argument, but I think whatever you got would be very unsatisfactory.
So you couldn't get some constant in terms of the expansion of geometry in different places?
You could get something that said, like, let's suppose that I have bounds on all curvature, like all derivatives of curvature and the diameter, but that's just another way of rephrasing that, like, whatever, that class is compact. And so I could take a worse example. But that's not, I don't think you can do anything that's, like, actually interesting beyond that.
But it's still effective. There's a question whether or
No,
not it's logically effective or not.
I think it's not. I think that it's you're using contradiction in that.
You don't know how large.
Well, it's not a contradiction, but yeah. You say assume that you're assuming that you only get this control. Well, maybe there's something there. I'm not sure. So let me not try to.
The way you were saying it seemed like it was a bad practical statement, but logically it was effective.
Okay, maybe I think that's probably true. Certainly practically it's not clear. Okay. So, all right. So, but if we want to move on to bigger volumes besides just tiny volumes, and what's the reason for maybe trying to do this? If our goal is to sort of understand scalar curvature, and what we're trying to do is sort of say how does scalar curvature act at a distance, right? That's sort of going to be the thing, right? So the previous result really.
Influence or what?
Yeah. No, I'm not sure. What is it? How does it affect things that are not just at one point? So in the previous result, it really was only affecting itself at one. There was only an effect at one point, right? Because you use this global argument, but then at the end of the day, the scalar curvature arises in the way that you expect, right? So the scalar curvature arises precisely as the expansion of the volume and area, which is that was our definition. So. Okay, we set ourselves the challenge of saying something about larger volumes.
So what if the
Yeah. So, in that theorem, so that actually you can look at the higher order terms in the expansion, and so then there's
No, not in that theorem. What you're saying, how does the scalar curvature influence global properties?
So
If it were constant.
it doesn't help. So, okay, so let me compare two theorems.
So it means the statement that there actually are always small balls where the boundary is actually CMC. It's
What's that mean?
Constant mean, it's a critical point. So, is
not,
that?
I mean, certainly that you don't typically expect the boundary of a ball to be
Sure.
CMC.
So certainly these regions are not coordinate balls. They're perturbations of coordinate balls. I don't think it's probably not true.
So that was the part of the statement I was just trying to make sure I
yeah.
understood. So
Sure.
you're saying it's approximately a ball, but it's not.
Yeah, exactly. Yeah.
Yeah. So it's approximately. That's not just a wiggly.
The wiggly genus. Okay, so in general, so the one I want to make is, so scalar curvature doesn't, okay, I'm now asking a question which is suddenly too broad. There's no hope to answer this question. So with Ricci curvature, whatever that is, right, the untraced version, so you have non-negative Ricci curvature, you can at least, you can't, okay, because the space of manifolds of non-negative Ricci curvature, there's no hope to describe the Iso-Parametric region because that's a huge space. You can't even write down the general metric, but there's no, but you can at least describe a bound for the area of the Iso-Parametric region of volume V, right? So if you have non-negative Ricci curvature, you can do no better than Euclidean space, right? And this is sort of related to the thing I discussed about the volume comparison for a region. But for scalar curvature, for example, you can give examples where the area will end up being very big. I think you can sort of build a tree of spheres. Scalar curvature is, non-negative scalar curvature is preserved under disjoint, or connect sums of manifolds. So you can sort of, you expect to be able to do things where this sort of example is very viable. So, okay, so since I've given up, I've given up on describing general manifolds, but I want to say something about the scalar curvature and the Iso-Parametric problem. And if you think back to what the key input to my previous, not my result, the previous result I talked about, is that the manifolds are.
Dimension 3 and higher, you do this tree of spheres,
Yeah.
not 2.
Sure. In dimension 2, so in dimension 2, scalar curvature is the only curvature, or classical curvature, and it controls everything. So we only really, the only time that this dichotomy really makes sense is in 3 and higher. And so I really use strongly that because the manifolds are nearly flat at small scales, small Iso-Parametric regions behave like I could do this limiting process. So what I wanted to talk about today is, so if we want to look at large volumes, maybe let's give ourselves some help and allow us to assume that the manifold at large scales is flat, is approximately flat. Okay, so so I've set this story up in a certain way, and there's sort of I could have started the talk from a different direction, and so there is a nice and very beautiful long story about the relation between general relativity and, more specifically, Einstein's equations and these sorts of manifolds, and specifically there's a surprising relation with scalar curvature. Okay, but I think I'll stop there and I won't mention this anymore because that would then take the next half of the talk to explain that later. Okay, so there are some additional motivations, but let me just pretend for today that this is my motivation. And so, for me, today, the main result will anyways only be about 3 manifolds. And so what I wanted to talk about are sort of asymptotically flat 3 manifolds. Okay? What this means is that I take a 3 manifold and I allow whatever happens in some compact region, no restrictions. It should be complete, right? So I mean, if it's compact, this region will be complete. But then, as I go off to infinity in some coordinate, there's a specified coordinate chart. So if I go off to infinity, the metric becomes Euclidean, along with some derivatives. Let me not say exactly what I do. Okay, so here we see that for such a metric, because we're flat at large scales, maybe we have some hope to describe the large Iso-Parametric region. Okay. And so indeed, that is the theorem that I wanted to talk to you about today. And so our theorem says you take a 3-manifold, which is asymptotically flat, like in this picture, and we're going to assume it has non-negative scalar curvature. Okay, so we should somehow have some scalar curvature entering.
It's a good picture anymore.
What's that?
Not a good picture anymore.
Well, this actually could have non-negative scalar curvature.
Really?
Yeah.
Dimension 3, so you could have a handle body. What's the?
Oh, that picture.
Yeah,
It's like S2.
Okay.
S2.
Yeah, okay, it's not a surface.
Okay. Yeah, that's a little too here there. Put all your curving there.
Sorry for any inaccuracy.
Okay.
Okay, so you could be flat. Okay, Euclidean space is sort of trivially asymptotically flat, right? And in Euclidean space, we know what the isoparametric regions are, but there's many of them, right? I can take a ball, but this ball over here is just as good, right? There's no difference from the point of view of the isoparametric. But if you're not flat, then what we prove is that for large volumes, right? So we only hope to talk about large volumes because that's sort of where the flatness is going to help us. Right? For large volumes, there's a unique isoparametric region, and I can really describe in great detail what. I mean, you can't write it down explicitly, but it's again, it's going to be the perturbation of some sphere, and I can tell you where the sphere is centered.
You want to use that positive scalar curvature as much as you can.
Yeah, so it's centered, for the experts, it's centered in the center of mass. Okay. So because I know some of you know a lot more about this than others, so I'll just say, we prove that the sort of the Huskian-Yau spheres are isoparametric. So that's all I'll say about it. But yeah, so there are some centers we pin down this. So I should say that there is prior work here. So Hugh Bray in his thesis proved it for the exact rotationally symmetric. So there's a very important special example of such a manifold, which is the Schwarzschild, Riemannian Schwarzschild. So it's the rotationally symmetric scalar flat manifold. Okay, and then Eichmair and Jan Metzger generalized Bray's argument to allow for some perturbation. You take the Schwarzschild metric and you allow not exactly rotational symmetric, but you still assume some sort of approximate rotational symmetry at infinity. And so what we do is we improve this to the best possible. So it's always dangerous again to make such a statement. From the point of view of a part of the story, we have the much weaker asymptotics. And so I should sort of explain that the difference here is a lot more than just sort of some tech. It's not you can't just like take the previous arguments and like generalize them directly. So the previous arguments were very like geometric somehow. You have some strong understanding about how the metric looks everywhere, and this lets you make some sort of just explicit. If the region doesn't look like you expect, you can just estimate this area and say it's too much, right? So that's no good. But with these much weaker asymptotics, the metrics turn out to be much more poorly behaved than infinity. And so, in particular, a big reason for studying these more general metrics is that there's these examples of by Carlotta and Shane, where so you have an asymptotically flat manifold. It has zero scalar curvature, but a half space is flat. Okay. And so these examples are quite interesting from the point of view of this sort of theorem because they contain critical points they contain infinitely many critical points for the isoparametric problem. Right? So any round sphere over here is a stable critical point, even locally minimizing for the problem, but it's not. But we prove it's not the minimum. So that I think is sort of a surprising maybe feature of this sort of result. Okay, so I want to talk a little bit about the proof and just sort of explain where the difference is in some sense, where between the two sort of the small regions and the large regions. So, okay, as before, you start with a reasonably large isoparametric region. So it's not. I should say that it's not even obvious that they exist. But let me just for the talk assume they do exist. So, okay, I'm going to keep taking bigger and bigger ones. Oh, and then it's got
So what are you
yeah.
assuming that makes it not Euclidean space?
So I say either it's flat,
Oh,
or I have my theorem.
okay.
Oh. All right, so my isoparametric region has gotten quite large, and you already start to see, in my funny picture, you've already seen, I think, a key difficulty of this problem versus the small isoparametric problem. And the point is that this flatness, in here, the frame in which you have flatness at large scales is fixed for you. I can't sort of, if I take a sequence of points going out to infinity, then I don't quite look uniformly flat at infinity. Like if I center myself here, these points are quite far away and they're very not flat. Okay. So, but in the small scales, I am allowed to choose which point I zoom in. Okay. And so this sounds like sort of a technical issue, but it really causes like a huge disaster for analyzing these regions because, and I'll come to an example of like the worst that could happen because of this, but let me just say, so this is what I just said, so in asymptotic with asymptotic flatness, you're only allowed to rescale around the center of flatness. So like, I don't think
What is rescaling you're talking about?
so I imagine making everything closer. So I scale the metric.
Scaling the metric.
Yeah. So if I sit here and rescale, then everything becomes closer. So there's still quite a bit of bumpiness near me, but if I go 10 feet,
You're good.
then I'm great. So, but the problem is that I'm only allowed to rescale around myself, and where I sit can't depend on the isoparametric regions anymore, like it did in the old problem. And so it's still true that when you rescale the larger and larger isoparametric regions, you can use the Euclidean. You're becoming Euclidean, except for at the center of rescaling where all this craziness is happening. You become Euclidean, but now sort of the Euclidean isoparametric region may not play nice.
You may not be inside.
You may not be inside, or even worse, somehow the worst possibility is that the boundary looks like it's going through this point, which is supposed to be the center, where I'm rescaling. Right. So
You want to be well inside.
yeah, so you can imagine that somehow here, whatever error I get from trying to do this previous sort of argument, like the effect of scalar curvature in the previous theorem was only at a certain point in the expansion of the right. And so if the error becomes too large, that sort of expansion is just totally going to break down. And so it turns out that so you really need to sort of have a completely new way of understanding these regions because you really don't even know. You can't even
You're not
say.
going to prove that the region is that you're inside. Your center is inside.
So yeah, so in this picture, what I do prove, although I won't do it for you today, is that the center is at 0. And once you know that, then you can
So
sort
you are
of
going to prove the center, the a priori center is inside the big parametric regions.
that's what I do prove.
Yeah. Okay.
Yeah, I won't prove it. I don't think
But
I
if
have.
you could assume you were inside of a definite factor, it would be a lot easier.
Yeah, exactly. Then it would somehow be quite analogous to the previous result. So here you have this real issue where these two scales don't align, right? The size, the area scale and the distance scale are not. When they break down, then it's quite bad. So okay, so I should say I'll say a word about the proof, but I won't say very much, and I'll talk about one issue which might arise later. So let me just say a word. Let me say this first. So my analogy, maybe this is obvious by now, but sort of the analogy between the two issues is so you have a function which the value and the derivative is 0, and you sort of do this sort of rescaling. You get 0, and this tells you, as we know from our calculus class, that you sort of understand the function near 0. Okay, maybe you need some derivatives, etc. But so that's sort of like the small isoparametric problem. But then suppose you have some function which decays quickly at infinity, and you try to do this other rescaling, which you blow down the functions, I would say. So here you do converge to 0, but you have this singularity of the convergence is not nice at the origin, right? Because you're somehow getting rid of all this information about the function in the convergence. And you don't really get, this tells you sort of nothing about the compact region, which is going to sort of play an important role in this sort of problem. So, okay, let me just I'll have one slide about the proof, which is a little bit technical, I'm sorry. So, the approach of what we do is to use sort of a geometric flow to analyze the isoparametric ratio. So we have this, so the x is supposed to be the center of rescaling, and this outer shell is supposed to be the isoparametric region. And what we do is we flow it inwards using mean curvature flow. Okay, so you flow by some curvature. So it's sort of a geometric heat flow. And it turns out there's an amazing observation by Huisken that along this flow, you can control how the isoparametric ratio, say, changes. So you can say, you know that the ratio doesn't get too much better. And you can control that based on something that's the bending of the surfaces of the flow. And so in this red region, we don't know too much about what's happening because these guys are exactly the ones that go through the center of rescaling. So this is quite the singular part of this process. But then once we've disconnected, right, at some time, the flow jumps over the center. I mean, it doesn't jump, but it sort of eventually disconnects. And then it just starts to flow nicely. And you should imagine that, right, I said, because we've rescaled, like this bit is we're fine. We're 10 feet away from the center, it suddenly becomes very flat and very understandable. So here, we behave like Euclidean space. And here, these guys, this is somehow where now the scalar curvature enters in a very roundabout way. And here we have to use another flow to understand the bending of these surfaces, which is inverse mean curvature.
You don't like that thing on the right.
Well, exactly. And so what happens is this blue region, I understand very well, but also what I can prove is that it contains too little volume versus an example I can construct. So you'll notice that if I'm sort of off-center, there's a big blue region, and the blue region is sort of Euclidean, and basically the theorem says, like, if you're not Euclidean, you can do better than Euclidean. So you see here, there's a big blue region, so you're very Euclidean.
So it's not good.
Yeah, so it's not good. So that's sort of what I just said. So, okay, I don't think I want to say anything more about the proof of this theorem, but instead, what I wanted to do in my last few.
So that means it doesn't jump over that center somehow.
It sort of
jumps over the center.
It might jump. Well, so we actually work with a weak flow, so it could jump.
I mean, keeping isoparametric near the isoparametric thing, it doesn't jump over the center. It's what you just outlined there.
Yeah, exactly. Yeah, exactly.
So it's inside the center.
Yeah, I think so. So, okay, so instead of talking more about that, I just wanted to end with one.
So did you already use the positivity of the scalar curvature?
Yeah, so it snuck in there because we needed a bound on the Hawking mass out here, and that uses the sign of the scalar curvature. It comes in such a roundabout way that it's not certainly. If you ask, what if you just drop the sign of the scalar curvature in the statement of the theorem, then the theorem is definitely false. If you then ask sort of, what about if you assume the mass is positive but you don't assume anything about the scalar curvature, I'm not totally sure. So it's a sort of a roundabout way of using scalar curvature. So in some sense, I lied a little bit, and it sort of has more to do about the mass, but certainly the proof does make definite use of sign of scalar curvature. So, okay, so what I wanted to finish with was sort of the worst thing that could happen is, And the worst thing that can happen, I'm saying that maybe the scale of my large Iso-Parametric regions, the distance to the center is very slow compared to the area. Right? So that's sort of how they aren't compared. Like I'm maybe drifting, like the distance to the boundary is very small compared to how big the area is. Okay? And sort of the worst thing that could happen is that I get really big, but the distance from the center of rescaling to the boundary is bounded. Say. Okay? So it turns out, I won't explain why, but so you could take suppose that you sort of always have a bounded distance to the center. It turns out that the limit of these boundaries, in some sense, becomes an area minimizing surface. So the Iso-Parametric problem sort of are about things which minimize area with a volume constraint. But here, the volume becomes infinity, and somehow the volume constraint can be deleted after the volume becomes infinity. Okay. So this happens in Euclidean space. Okay. So Iso-Parametric regions are balls, and you can sort of pick the centers correctly so that you limit to the plane. And the plane minimizes area among all sort of compact changes. Okay. And so if remember, I would like to show that the Iso-Parametric regions have centers comparable to this sort of center of rescaling. And this is like the worst example of that not happening. So what I see from this is that if I knew that in this manifold there were no area minimizing surfaces, then this sort of thing couldn't happen. Right? So this is the most basic thing you could say about comparing the two scales of Iso-Parametric regions. And so I wanted to close by just sort of briefly discussing this is actually earlier work with Eichmair. And so what we proved is that, again, take asymptotically flat, non-negative scalar curvature, and so assume that there is an unbounded area minimizing surface. So we don't assume that it comes from the limit of Iso-Parametric regions. Okay? And so in that case, the only way that could happen is if you're in the flat Euclidean space. So in Euclidean space, the planes are unbounded area minimizing surfaces, but that only can happen in that situation. Okay. And so here there is all right. And so then a related work, which is not on the archive, so I thought I'd mention it. But so if you drop asymptotic flatness, then there's sort of a different. You need something a little bit more to conclude some sort of rigidity. And it turns out that if you have a cylinder, then you should imagine there is an example. If you take the product of the flat cylinder across R, the cylinders are all area minimizing. But somehow, so we prove, the related thing. This is supposed to be the word.
The picture doesn't tell us what you mean.
Oh, sorry.
What do you say?
So you take a cylinder across R, and then but a flat metric across here, and then the cylinders are all area minimizing. That's not too hard to prove. And but this is the only example. And this guy is flat, so it has non-negative scalar curvature. But this is the only example of an area minimizing. And so I'll just finish. So this is related to some work of Anderson Rodriguez and Gangdu. And so there's also, if you put torus instead of cylinder, this is an old theorem of Kai Galloway. And I'll just have one more slide. So the difficulty of such a theorem is that you want to use non-negative scalar curvature, and you'd like to, one way to sort of try to prove this thing is analyze, say, the distance. If you have an area minimizing surface, you could try to look at the distance from the surface, for example, something like that. And if you have some control on Ricci, you know something about the distance function. But scalar curvature tells you nothing about the distance function. And the second difficulty is that because the surfaces, you'll notice that the previous page was about the surfaces that I had and I cared about, they were non-compact. So it doesn't make sense to talk about their area. And so the area turns out to be something which is sort of well controlled by scalar curvature in a way that it goes, this is sort of the original, one of the original results about scalar curvature. It goes back to Shane and Yao. But because you're non-compact, you start having some serious difficulties under using the quantity area because it's infinite. So that's a big difficulty. So I won't say anything more here. So I think that's.
So the scalar curvature keeps the center inside.
Yeah. So
And then the next argument about boundedness keeps it far away from the boundary.
yes. So okay. So what I'm worried about is that. So this is the theorem basically. The theorem says that this is how the isoparametric regions look, and the argument that I just discussed says that they don't look like this, sort of. And there's some intermediate range which is even more like difficult, and you really need the flow, where this distance, so the argument I just described very quickly says this distance is unbounded.
Yeah.
But if you look at like the distance versus like a square root of the area, right? Both of these are lengths. And so if these are both comparable, then you hope to just be able to analyze by using something analogous to the small isoparametric region theorem. You should be able to use analysis to estimate everything. And you've got a good estimate, and you say only this can be the best. That's by something like saying you want to center at the point of greatest scalar curvature. But if the distance is very slow, then that's really where you need to sort of hook up like a new way. Yeah.
Is the reason you restricted dimension 3 because of the inverse curvature flow? Do you expect this to hold at higher dimensions regardless?
So the second part of the question is I think it should hold. I mean, there's good reason to believe that in higher dimensions the same theorem is true. At least up to dimension 7. I don't know about. I'm not exactly sure about higher. There's actually a couple places where you use 3 dimensions. The first is, the most serious is inverse mean curvature flow. And then there's a sort of like sorry, wrong way. I lost it. Where's my picture? Oh, here. So there's also a technical point, which is, so in higher dimensions, you wouldn't want to use mean curvature flow. You'd want to use like a flow by power. There's a paper by Felix Schulze that sort of suggests the right flow here. But it's actually it's quite a difficult technical point to say that you know that you start something which is close to a sphere, and you flow it, and you want to say that sort of, for example, in the limit, it was just a shrinking sphere, and it's not totally clear, although I think this could be overcome. It's not totally clear how to do this, take the limit for the h to the k flow, because here it's like a Brachy flow, and you have these nice compactness properties. And the higher dimensions, there's some technical issue to solve as well. But really, it's really the inverse mean curvature flow. That's the key.
So when it comes to the local result, I know that's not...
Sure, yeah, that's all right.
So you say that that your isoparametric sets are close to small geodesic balls. So suppose that we have a manifold and have the unique point of maximal scalar curvature, so you know uniquely where you're scaling. You didn't quite say what you mean by close here, but presumably there's no reason to expect any kind of uniqueness, even if you have a unique point of maximal scalar curvature.
So I think that I should be careful here, but okay, don't quote me on this, but I believe that if you have a unique point of maximal scalar curvature, there should be a unique isoparametric region. And the point is that you actually have a very precise description. So like what you can do is you look at all small geodesic balls, and then you perturb them as close as you can to be critical points of isoparametric, so to have CMC. So this is what's called as the Lyapunov Schmidt reduction. So sort of what you're doing is because the problem is that you have an isoparametric region that looks like a ball, but it's close to many geodesic balls. It's not, I don't know what do I mean by that, I haven't been very precise. So you should really fix a center, like you should pick the best center. And then actually it's it's even much closer than it looks. So, and at that point I think you do really know some strong uniqueness. And so like at the very least, you can very explicitly describe what it looks like. And obviously there's some estimate you don't know. You throw some terms away, but you have a very good idea of what it looks like.
So you said that if your thing is not flat, you can have an area minimizing unbounded.
Yeah.
But what about on this thing that has a flat
So
surface?
that's a very good question. And I think, sort of that's surprising about this result. And it says that the thing so let me just say the question.
Repeat the question.
Yeah, so the question is, okay, so there's, let me just find the theorem again. Everyone's gonna be sick. So the question is, how do you reconcile these two pictures? Okay, so there's a picture where I say that if you're asymptotically flat, and again, the point of this result really is that the assumptions, when I say asymptotically flat, it's sort of as weak as you can get away with it, I think. Again, it's always dangerous in such a state. So they're very weak, and in particular, it contains these sorts of metrics, which satisfy the asymptotic flatness, and they have zero scalar curvature, so that's even better than non-negative. Okay, but they have half space which are flat. So you can put in, well, let me put it this way. There is this plane. And so you can ask, the plane is certainly a stable critical point for area, right? If you do any local perturbation, you remain in the flat space, and it looks like it stays flat. But it turns out that, the theorem doesn't really construct the competitor explicitly, but if you go far enough out, and you look on the plane, and you say, was this the least area surface? Well, the answer is no. It's better to sort of go in and like this. And somehow, this, if you haven't thought about this much, it's quite surprising. But I think that if you think about it a little bit, so area is sort of like the Dirichlet energy, right? Like the area of a graph, for example, is well approximated by the Dirichlet energy. And so if you know the fundamental solution in 2 dimensions is the logarithm, and sort of the logarithm lets you go a huge amount of distance. Okay, it takes a long time, but you can go a huge amount of distance while paying very little in terms of area. So like the height can increase quite a bit while paying very small amount of area. And then what happens is somehow you pay a bit here to make this height bigger. And then this part, for whatever reason, I can't say, well, I don't know exactly why, but the non-negativity of scalar curvature guarantees that there's some region here which you've gotten there, now you get your payday, and you do much less area. So it's sort of indirect argument. But there is, all I know is there is such a competitor.
Where does one find these examples?
So there's a recent paper. So Carlotta and Shane. I think it's in Vincianus this year. Yeah, it's sort of a gluing thing. And so, since I think you know the the point of these is that, so like, so these metrics, they've proven exist with decay rates like r to the minus tau. So tau had better be bigger than 1/2. That's sort of the right number in 3 dimensions. And they get all the way up to 1, but not quite. 1 is sort of like the short shield of 3D.
Yeah, what worries me is that when you do gluing and then solve Yamabe-Laplacian, analytic continuation is going to make the formal factor bleed into the flat region. So
I think they do it in a different.
they must do it in a different way.
It's sort of related to the Corvino rule.
They use the scalar, they use the Hessian equations. So not just the Imavi equation. They have a-
Yeah. It's not a conformal
It's an
block.
undetermined system. So that's
Right.
undetermined is
Right,
what
right,
we're
right.
using.
Oh, okay.
All right, let's take on